Hello, everyone. Welcome to the session. My name is Joshua Robinson. I'm with Pure Storage, and I'm going to talk today about high-performance input pipelines for deep learning training. Basically, an input pipeline is all the work that you need to do to get your data to the GPU before the GPU then does its magic to build a neural network. So before I start with that, I want to set a little context about why this is important, and then give an intuition about what is an input pipeline really doing, and then finally present some of our benchmarking methodology for how to find performance issues and debug them in an input pipeline. Here's my clicker. So the first question I think to answer is, why is a storage company talking about AI? Well, what if I told you that storage is the most important part of AI? I'm getting skeptical looks, that's fair, because in actuality, data is the most important part of building AI, deep learning. And of course, as a storage company, we're intimately associated with the data, but it's not fair to say that storage is the most important part. Data is. Just to illustrate that, this is the Google Director of Research, Peter Norvig, making the claim at Google, they don't have better algorithms, they just have more data. And this is, in a lot of cases, true. The success of an AI project really depends more on the data than the actual algorithms used. I find it really useful to borrow this hierarchy of needs from a well-known data scientist, Monica Rigatti, that really talks about the fundamental building blocks for a successful deep learning or AI project. What this really means is, at the bottom of the hierarchy is ingesting your data, collecting your data. And then above that, the preparation, doing transformations, cleaning your data, labeling your data. And then above that becomes the algorithms. And then finally at the top, model validation, A/B testing. Frankly, most people aren't at the top layer of this pyramid yet. The idea here is it doesn't make sense to start experimenting with algorithms, using a fancy convolutional neural network, until you have the data to work with. Because what will happen is if you have a really sophisticated neural network and you give it 10 pictures of cats and dogs, what it will do is just memorize every single pixel in those images. That's not going to give you a valuable answer. You need a proper sized data set to actually evaluate your algorithm. So the bottom two layers of this, data ingest and data preparation, are all about the data set. And that's the fundamental importance of data, where you build on top of that. You build on top of your data set. Point the right way. Now, we all know that AI is a generic term. It's been used multiple times, meaning multiple things, and it comes in waves. And we're currently in an upswing with a lot of new successful use cases and applications of deep learning specifically. Some of the commonalities in the winters is that the technology, the compute, the storage, the hardware, the data couldn't keep up with the algorithm's needs. And the result was hype. But in these rebirths, there's a focus on specific problems, so specific problems that algorithms like neural networks can solve well, and availability of the compute hardware and the data. So what I mean by the compute hardware is GPUs from NVIDIA, for example, that allow you to do computations dramatically faster than you could previously. So in deep learning specifically, the advantage for data is you can give these algorithms more and more data, and they will continue to improve. This is a really important distinction with classical machine learning models, where it topped out in terms of accuracy much lower. So what that means is I have 10,000 training set samples. My model gives me an accuracy of 90%. And then if I doubled the number of training samples, my model might not actually improve any because I've already reached the maximum accuracy of that model. But with deep learning, we've seen that those scale keeps going. Currently, the rule of thumb seems to be about a logarithmic scale. So to double your accuracy, you need 10 times as much data. Google recently took the Imagenet benchmark, which is 1.3 million images. I'll talk more later about that. And they said, hey, we have Google image search. There's 300 million images in our data set. What if we use the same exact algorithms and train them with our data set? No changes to the code, just more data. And not surprisingly, they were able to get better accuracy just by having a lot more data in this case. So data is crucial, and it goes well with these deep learning techniques. So an intuition behind what's happening when you're training deep learning. So I'm going to use a simple example of image recognition. It applies to most problems, not all, but most problems, and it's actually the easiest and most intuitive to talk about. So I'm going to focus on, frankly, cats and dogs, determining those two for explanatory purposes. So the intuition is, you start with an image of a dog, your deep neural network performs some calculations, and the output is a dog. But what was really happening is you have a set of matrix multiplications that happen, and at the outcome you have probabilities of what type of object is in your image. And it's these matrix multiplications that GPUs are really good at. So once you get that image of the dog on your GPU, it can fly through those calculations. Now, each of those different layers can be associated with primitives, rough shapes, macro features, and that's really the heart and soul of these neural network algorithms. I'm not going to go into detail in those today. I'm going to focus more on getting the data into the GPU. So when you're training a model, you need to learn from your mistakes. So what that means is, once you've calculated the prediction, you also need to have the right answer available. So you can say, well, I got close, and then I want to calculate the gradients, which means, how could I have gotten a little bit closer? You effectively want to nudge your model in the direction to get closer to the right answer. And then you make changes to the model to move in that direction. Again, very high level. Now, at the end of this, you can train a neural network, but this is one process. And for large neural networks, if you're just doing one image at a time, this could take a long time to train. So what's really key is having a scale-out approach to training a neural network. When you're doing this with a data parallel model, what you're effectively doing is multiple of these operations in parallel, but now you add a new step, the merge gradient step. So this basically means multiple GPUs independently do a calculation on a different image. They get their own answers, and then they exchange answers. They share, hey, I got this result, what did you get? And then they basically average those answers and apply that as their update. So when you scale out, now you have multiple different GPUs doing this computation. And again, more data needs to get into those GPUs. But as long as everything scales out, you can get a linear increase in your training performance by adding more GPUs. Again, this is the promise if everything scales out. Ideal world is I have lots of data, and I have lots of GPUs, and the data gets to those GPUs. I can imagine you see where this is going. In reality, there can easily be a bottleneck here, getting that data to the GPUs. And that's the input pipeline. And that's what I want to talk about for the rest of this presentation. This, on the right, is a TensorBoard diagram of ResNet, well-known image recognition algorithm. And what this is basically doing is diagramming what that network looks like, the layers of the network, the size, what they're doing. And this is from the paper, and this is understandably what the paper focused on, because that's the research. What I'm interested in, though, is that top box, the very first box that says image. That's basically getting the data into all these layers, right? When you look at the paper, gosh, that looks simple. There's just one box, one word. Can't really be that simple, right? So if you zoom in on this, it's not. This is what that input pipeline looks like. There's actually a lot of things going on there. And I have yet to find anyone who can just look at these and say, oh yeah, your bottleneck's here. It's not intuitive, at least not for me yet, even after looking at these for a year. So what happens if there is a bottleneck? Your GPUs will sit idle. You may have 32 GPUs, but if each GPU is only active 25% of the time, because it's waiting for data the other 75% of the time, you might as well really only have 8 GPUs, right? So there's real consequences to these GPUs being idle if that input pipeline is starving them. All right, so because this is not particularly easy to understand, I want to walk through an intuition of what is actually going on in here. And again, I will use the image recognition example. So there's really 5 steps that happen in this input pipeline. The first one is simple. You're just enumerating your data set. What is the data that you have available to train? This could be in a file system, in an object store, in a database. And you could have tens, hundreds, billions of objects, hundreds, millions to billions of training samples in your data set. So step 1, just find out the size and the items in your data set. Step 2 is to associate labels with those data set points. This is the step where you associate the right answer, which you know from some other process, whether it's a human labeling the data or you have another automated process which provides labels for the data. So now you have your training data, the raw data, and the answers. Sometimes these are, or often these are stored in a separate place, so they need to be joined together. And both these steps happen once for each training run. So depending on the length of your training run, the performance of these may or may not be important relative to the overall training operation. The next step you do is shuffle the data. This basically means to randomize the order of your data set. This is actually a really important step because it prevents you from, or prevents your network from learning artifacts in the data. Learning ordering that's just an artifact of how your data set is laid out. So it learns, oh, I see this picture of this dog, and then I always see the picture of this cat next. That's not actually something you want it to learn, so you shuffle your data. Of course, from a performance perspective, this shuffle operation basically makes any kind of caching not work. This is the worst case scenario, in fact, for a caching system, randomly shuffling the data. So you shuffle the data. The next thing you do is you do transformations and augmentations to the data. So in an image case, you're decoding a JPEG, you're cropping it, you're adding some distortions, you're making some changes to the data. And this again is important because what you're really doing here is making your data set look larger because of the importance of a large data set. So you make your model more robust by showing it slightly different cropping approaches to your image, or adding some blurring, or doing a rotation of your image so it learns in a little bit more robust of a way about your data. So you apply transformations to your data, and then finally, you copy the data to the GPU to do the matrix multiplication, the neural network part. Fancy animation, which I did not build because I don't know how to do that. And then when you're training, you're actually doing this on repeat. So you go through your data set multiple times, not just once, and you repeat steps 3 through 5 for each iteration across your data set. So again, this is important. You need to reshuffle every time through so that you don't see your data points in the same order as last time. And this has been shown to create more robust, less overfitting, better models. So you do your distortions, again, differently, because each time if you do slightly different croppings or slightly different rotations, you're again creating more robustness in your model. So there's value in redoing these operations for each iteration. And then again, copy the new data set to the GPU. And any of these steps can be a performance bottleneck. In particular, the bottom three, because they're repeated for each iteration of your data set. So if you're doing 40 epochs through your data set, you shuffle and you transform each image 40 times. Now again, I focused on the nice, easy to explain cats and dogs. Most other domains follow similar-ish patterns. It's not always the same, but this gives you a rough idea of the kinds of things that happen in an input pipeline. So now that we have a better understanding about what's happening in input pipeline, I want to talk about some work we've done benchmarking input pipelines and how we've found going about finding bottlenecks in that input pipeline. For this, we've used the Imagenet dataset, which again is 1.3 million images, 1,000 categories, and it's, as far as we can tell, the most commonly used benchmarking dataset for deep learning. The hardware you use actually on there is 4 NVIDIA DGX1s, so 32 GPUs, all connected with Ethernet to the storage system, which happens to be the storage system that we build, but again, that's not the point of this talk. And those 32 GPUs provide us the opportunity to speed up our training performance by 32x. So that's the goal. And I'll talk about why it's not particularly easy to achieve that. Oops. Quick overview of the software stack. We're using TensorFlow. We're using Horovod to do the distributed training. And we're using this standard containers that came through NVIDIA Cloud. So the first thing we do is we do a training operation with 1 GPU. We use the default settings. We just want to calibrate what kind of performance are we going to get. The answer is 216 images per second, or processed through the training phase. It's great. Is this any good? Is this bad? How do we know, is this a good result or not? How do we make sense of this? Well, the first thing that we do, and what's commonly done, is we replace the input pipeline with synthetic data. This is a really powerful approach, because what you basically do is you make up random noise in memory, in DRAM, and you use that. So you effectively now idealize the entire input pipeline. Creating synthetic data in DRAM is very fast. Now, at the end of this training operation, the results you get are going to be worthless because you're training on random noise. But the valuable part here is that from the perspective of the GPU, it does all the same calculations. It does a lot of work, it gets nowhere in the end, but it gives you the opportunity to measure how fast the GPU can operate, because it's still doing the same amount of work regardless of what data source you're giving it. So when we did this approach, use synthetic data, we got 228 images per second. So a little bit faster, 12 images per second faster. So that gives you an idea of what we're losing from that entire input pipeline. So we have a start to understand the performance impact of that. But we can apply some standard approaches, like prefetching the images. So while we're doing the processing, we start prefetching the data for the next iteration. Again, a standard approach, nothing particularly innovative here. And we get up to 225 images. So now we're only 3 images short of this idealized synthetic number. So that's less than 5% difference. Should we really care about this? Is this important to continue to try to optimize and get even better? Well, the answer is, of course, yes, because this is only 1 GPU. So now let's scale out and see what happens. So when we go to using 32 GPUs together, we're getting 4,100 images per second. And our synthetic test with 32 GPUs gets 7,200 images per second. So now that we've scaled out, that 5% gap has gone to a 42% gap. Now we really do care about that. That's a big deal. So again, let's apply the benchmarking methodology of replacing parts of an input pipeline with a perfect equivalent. So, sorry, 7,200 images a second is the linear scaling. I didn't explain that right. What that means is it's literally 32 times the performance of one GPU. So that's with perfect linear scaling, which we know is unachievable, but it's still our goal. With synthetic data in 32 GPUs, we're able to get 6,500, close to 6,600 images per second. So that's a much more attainable goal from an input pipeline perspective. So that gap between 6,580 and 4,100 is really the impact of the input pipeline. The gap between 7,200 images and 6,600 images, that linear perfect and the synthetic data, is actually due to the overhead of that gradient exchange phase, where the GPUs exchange their answers. This is what uses the NVLink high performance connectivity inside the DGX1s. But I'm not going to focus on that. I'll focus on the input pipeline that gets us to 6,580. Again, we apply the well-known best practices for these pipelines, adding prefetch. And that gets us a lot, up to 5,300? Yeah, 5,300 images per second. We're still quite short from that 6,580. We effectively did an exhaustive search over dozens of parameters in TensorFlow just to find out what minor tunings could slightly increase that number. And there were a few things like tuning the thread pull limits that got us a little bit more gain, but really we weren't able to get significant more gains with all of those input parameters, those tuning parameters. What we did find is that if we disabled distortions, so that one of the phases I mentioned in step 4 earlier, if we disable this phase, we're getting much closer to that synthetic benchmark result. Now this is interesting because it means that work we're doing, cropping, rotating, adding distortions to the images, is having a big impact, which actually means it's the CPU on those GPU servers that's the bottleneck. This is very interesting because we know there's a lot of work being done to move these transformations onto the GPU so that you can also do this work on the GPU more efficiently. And this is very good motivation for why that's important, to be able to move these steps onto the GPU. Now again, we wouldn't want to actually use the neural network trained without distortions, because they were there for a reason. They made the network more robust and more general. But this technique allows us to identify that bottleneck. Same with the synthetic data. We would never use that result, but the approach lets us understand the bottlenecks in our pipeline. So we're close to that synthetic benchmark. And one thing that's very interesting to me is, so we started this project at about 11 months ago, and what we've observed is there's been a 2.5x improvement in performance just in the base software of TensorFlow over these 11 months. So these results are 4, 8, 16, and 32 GPUs with full tuning on the same hardware. So it's really just checkpointing the software 11 months apart. And you see, on average, 2.5 times improvement. And this is all due to, again, because it's the same exact GPUs, software improvements. And this really highlights the importance of, one, just keeping up to date with the new releases in this very fast-moving area. And two, the importance of the input pipeline and the software aspects of it that do the transformations and prepare your data for the operations on the GPU. So the software stack continues to improve and lets you train these models significantly quicker if that input pipeline is not a bottleneck. Now again, these are with significant tuning applied. These results are with significant tuning applied. This is not the default out-of-the-box behavior. And we look forward to seeing more of this kind of progress as we're able to transform more of these operations, like the distortions, onto the GPU. So at the end of this, we have a methodology for evaluating the potential bottlenecks in an input pipeline and getting the data to your GPUs in a scale-out environment. We think what's valuable here is that methodology of replacing parts of the input pipeline with idealized equivalents so that you can understand where the performance bottlenecks are. So this is the end of my presentation. I see mics here, so I presume that we can have questions. If anybody has any questions in the audience or wants to find me afterwards. Yes? Yeah. Yeah. So the question is basically, what about pre-processing all of the distortions? And that can be done, but the reason it's not done in environments that I'm aware of is that each iteration through the data set benefits from a different distortion. So for example, if you have 40 epochs of training, so basically means you have 10 million images and you go through them 40 times, each of those 40 times is a different distortion. And so while you can pre-calculate them, you're not really gaining anything because you need to do 40 pre-calculations. Or at least what I mean by that is the results have shown that your models are better if you do different distortions each time through your training phase. And so that kind of, if it's only once, there is a huge benefit from that because you get to amortize the cost over 40 epochs, but since you need to do it 40 times, you don't really get a benefit. Thanks. Any other questions? I think I got you done about 10 minutes early. All right. Thank you, everyone. Feel free to come find me if you have other questions.